In the last video, we discovered that transformers only work with AC because AC keeps changing direction. But how exactly does it change? How fast does it switch? And what kind of pattern does it follow? The answer lies in one of the most elegant curves in all of mathematics: the sine wave. A C electricity is a sine wave. It has 4 key properties that fully describe it. First, period. Second, frequency. Third, amplitude. Fourth is phase. And that's exactly what this episode is all about. So, let's dive in and ride the sine wave together. Imagine voltage on the vertical axis and time on the horizontal. Voltage begins at 0, then smoothly rises to its highest point, the positive peak. From there, it falls back down, crossing 0 again, continues to drop to its lowest point, the negative peak, and finally returns back to 0, completing one full cycle. What you see is an AC waveform, a picture of how voltage changes over time. The time taken by wave to complete one full cycle is called the period. We use the symbol capital T, and it is measured in seconds. So, if an AC current completes one full cycle in 1/50th of a second, which is 20 milliseconds, then T equals 0.02 seconds. But engineers care more about how many cycles happen in 1 second. That number is called the frequency. We use the symbol F, and it is measured in a unit called Hertz. 1 Hertz means 1 cycle per second, named after the German physicist Heinrich Hertz. The relationship between both is beautifully simple. Frequency is the reciprocal of the time period. If the period is 0.02 seconds, the frequency is 1 divided by 0.02, which equals 50 Hertz, which means 50 complete cycles every single second. In most parts of the world, electricity operates at a frequency of 50 Hertz. But in regions like North America, Japan, and parts of Brazil, the standard is slightly higher. 60 Hertz means visibly dances faster than rest of the world. Now, you might be wondering, why is the world split into 2 camps? Some countries using 50 Hertz and others using 60 Hertz. It is a historical accident. In the 1880s and 1890s, different electrical pioneers, Thomas Edison, Nikola Tesla, George Westinghouse, built systems with different frequencies. There was no international agreement. Different regions adopted different standards, and by the time anyone tried to unify them, too much infrastructure had already been built. But what does this difference actually mean in the real world? At 60 Hertz, motors run a slightly faster. Clocks that use AC frequency as a timing source were more accurate in 60 Hz systems. Fluorescent lights using 50 Hz can produce a very faint flicker at 100 times per second, though modern LED lights eliminate this entirely. For most modern electronics, laptops, phone chargers, televisions, the frequency doesn't matter at all. These devices use switching power supplies that accept both 50 and 60 Hz automatically. You will see 50/60 Hz printed on almost every device you own. So, we just learned that frequency tells us how many cycles happen every second. But here's a deeper question. What if we measure this motion? Not in cycles, but in angles. Because remember, one complete cycle of a wave is not just a loop. It's actually a full rotation of 360 degrees, or 2 pi radians. So instead of counting cycles per second, we can count how many radians per second the wave is covering. And that is called angular frequency. It's denoted by omega, and it tells us how fast the wave is moving in terms of angle. And the best part, it connects directly to frequency. Omega is equals to 2 pi f. So if the frequency is 50 Hz, omega is equals to 2 pi multiplied by 50, which is approximately 314 radians per second. That means the wave is rotating at 314 radians every second. This is why in AC equations, you'll often see terms like sine omega t instead of just time. Because electricity isn't just oscillating, it's rotating through angles. Now, let's talk about the height of the wave. That is simply the amplitude. For an AC voltage signal, the amplitude tells us the peak voltage, the maximum voltage reached at the top of each cycle. We call it VP. Here is something that surprises many people. When we say the electricity in your home is 230 or 120 volts, that is not the peak voltage. The peak voltage in a 230-volt supply is actually around 325 volts, and 170 volts is peak for 120. So, what is 230 and 120 volts? It is the RMS voltage, root mean square, and it is far more useful. Here's the intuition. An AC voltage that alternates between plus 325 volts and minus 325 volts delivers the same average power as a 230-volt DC source would. The RMS value captures that equivalence. The mathematics gives us a clean formula. VRMS is equals to a peak voltage divided by square root 2. And if we substitute value of 1 upon square root 2, it becomes 0.707 multiplied by peak voltage. 325 volts divided by the square root of 2 gives us 230 volts RMS. Exactly what your wall socket provides. This is what your multimeter reads and all devices are rated for. RMS is the real-world number. The last concept in this episode is phase, and it is one of the most important ideas in all of AC circuit theory. When you have a single sine wave starting at 0 at time 0, we say it has 0 phase, no offset. But when a second wave starts slightly earlier or later in its cycle, it has a different phase. We say there is a phase difference between the two waves. Phase is measured in degrees, from 0 to 360, or in radians. A phase difference of 90 degrees means one wave is 1/4 of a cycle ahead of the other. This matters enormously in AC circuits. A capacitor causes current to lead voltage by 90 degrees. An inductor causes current to lag voltage by 90 degrees. For now, the key takeaway is that phase difference is a time shift between two waves, and it is given by V of t, the voltage at any instant in time, equals peak voltage multiplied by the sine of omega t plus phi, where phi is the phase angle, which we will come to in a moment. This single equation describes all AC electricity. Everything, transformers, motors, filters, power systems, starts from this equation. Now, let's bring the complete picture together. Sine wave is the shape of AC electricity, amplitude is a height, period stands for time per cycle, and frequency is cycles per second. Last but not least, timing shift is given by phase. These all properties, together, completely define any AC waveform. If you enjoyed this ride on the sine wave, smash that like button, subscribe, and hit the bell for next video. We're diving into RMS values, peak versus RMS, and why your multimeter shows 230 volts when the peak is 325 volts. Drop in the comments, are you on 50 Hertz or 60 Hertz? Thanks for watching. Now go turn on something and feel the waves. See you in the next one.